This is the manual from the Siemens VI. It's very thick. Your manual is very thin. Very thin, yeah? So
you have two documents also.
Yeah.
You have two documents.
Yeah, that's right. This is
okay, I can read it twice, yes.
no, I mean you have all things inside of your it is enough for
when do you buy by weight? It's just technology.
yeah, I know, but
I'm not talking about weight of paper.
I wonder it is enough for the PLC program.
It's better to look inside, and then you can know if it's enough or not.
Okay, I will try to.
If you just okay, weight of paper.
Okay, I will.
These guys have made one regulator. I've made three.
Really?
Yeah, with this document.
You're still really. Okay, let's start.
Okay. So compared to, let's say, conventional regulators, the electrode regulator is an open loop regulator, not a closed loop. Because you see, you have the measurement on one side, and you send an order to the actuator on the other side. There is no feedback. No? Compared to, let's say, speed regulator in a car, you regulate the speed. So you take the speed, and you go through the PI regulator, and you act on the speed. So there is a closed loop. Here it's an open loop, yeah? Because there is no way to do anything else, because we have the measurements. We have the measurements. We have the measurements here on the transformer board, I mean on the transformer outlet, and we want to adjust the arc feature here, but we cannot measure anything here, yeah, because it's too hot and it's moving, so there is no way to measure anything there. And in fact, we want to adjust the arc length, yeah, but we can just here change the electrode speed. At least I tried in the past to develop a regulator based on the electrode position. And we made some trials, and it was not better than this kind of simple open loop regulator. So we decided to abandon this closed loop regulator, which makes the things complicated and relate and requiring, let's say, good sensors to know the position of the electrode. And the sensors is just, let's say, the cable with a drum, and the cable can be damaged easily. So it's not reliable. So this kind of regulator is the most efficient for the electric arc furnace and ladle furnace. So how do we do? You see here, we have the current measurement here, and we have the voltage measurement. This is realized by the TI directly of the transformer primary side. So we have to build up an interface to have the image of the secondary, or we install Rogowski coils on the secondary side to have directly the current. You know what is a Rogowski coil? You know, or you don't know?
Yeah, actually I have a question about that. I know that the CT transformer can do the same thing as like the Rogowski,
Yeah.
right?
Yeah, but the CT is like a shunt. And imagine you have to design a CT for, let's say, 60 kiloamps. It's going to be a huge CT. It costs a lot of money. So that's why the CTs are installed on the primary side. And the CT has a dead band. as a deadband for, let's say, to have, let's say, the RMS value of the current is enough. But sometimes you want to have the harmonic precisely, and in this case, the Rogowski coil is the correct measurement tool.
You mean the transient value can be measured by the Rogowski coil?
Yeah.
But you mean that CT cannot do that?
If you just want to have the RMS value of the current, CT is alright.
Then the CT can measure the value as RMS.
But if you want to have precise information on the secondary current, the Rogowski coil is the better measurement tool. And anyway, Rogowski coil is not very expensive.
요즘 다 로스키 거의 다 씁니다. 근데 로스키 거의 문제는 많아. 설명해줘서.
Can you display the Rogowski coil, the picture or something?
Explain. 그건 로스키 거의 스크린. 의미가 있는 건 아니고 러시아 사람이 우리나라 이름을 모르겠어요. 그 사람이 이걸 개발했는데 가르치더라. 그래서 포인트 써보니까.
This is every minute. Every minute. Every minute.
Can be mute, yeah.
Every minute.
When you have a when you have a wire with current, yeah, you have a magnetic field, yeah. Each time you have current in a conductor. So the principle of the Rogowski coil is to measure the magnetic field and have an image of the current. So Rogowski coil is just, let's say, something like this, small coils, yeah, which are surrounding the cable or the transformer pins, and here you measure here voltage difference, which is proportional to the derived of the current divided by the time. The advantage of this device is that this voltage differential is independent of the form of the coil itself. It means you don't need to have something very, very accurately designed in the shape. What is important is to have the number of coils here that gives you the report here of what you measure, yeah, compared to what is going really through, but it's calibrated normally. Yeah. So usually after this, you have an integrator, yeah, to recombine and to have the current. So you have the coil itself and electronic part.
And compared to the general current transformer, Rogowski coil has more wider regional frequency break range.
The deadband, compared to the conventional
Current
transformer, this is, let's say, 200 grams. Yeah, the CT is several kilograms. Eh?
Yes. But
And then it's easy to install. This is a cable thick like that with the
linear region from the point of frequency band, the linear
Yeah, it's linear.
linear region is more wide than a current general
Yeah, yeah,
current
yeah.
transformer.
Yeah. And anyway, it is designed for, let's say, 0 to 100 kiloamps without any saturation.
지금 그 위키피디아로 찾아보면 영상이랑 설명이 잘 나와 있어요.
And you have many suppliers. Huh?
Yeah, it can also more fastly respond to the current fluctuation compared to general
Yes.
current transformer.
Yes, yes.
그리고 설치할 때 잘 구워지니까 조심해서 설치해야 돼요.
Yeah, because in fact, by construction, yeah, the Rogowski coil is somewhere here, where the CT is here, yeah, on the primary side, far away. So you have a lot of impedance between this point and this point. So you don't measure the same harmonics. Which is for the, let's say, basic function of the regulator enough. Yeah? CTs are normally enough. But for advanced function, it's not enough.
Yeah, the frequency interpretation, we need the lowest quality. 맞는 것 같아요.
Where is the installation location for the Rogowski coil? Maybe the bus bar around the bus bar.
Yes, around the spot.
지난번에 가서 한번 나왔어.
It's better to have it inside the transformer room.
Inside the transformer.
Yeah, to get it protected from the fire of the furnace.
트랜스포머하고 세가닥 주간 사이에 그 설치하는 게 더 잘 부서져 저게.
But
영화탄 박스에다가 트랜스포머구나.
but a lot of time I've installed it outside even. Yeah. If you don't have room to get inside and to install it, you get outside. Especially when the triangulation of the transformer is done outside. Ah, yeah, 1 point. When you want, yes. Regarding the installation, most of the transformer now have external triangulation. Yeah.
In these days, internal.
Eh?
In these days, internal delta close.
The delta closure most of the time is outside.
But in these days, the POSCO groups use the internal and also the.
Okay. So, sometimes inside. Most of the time is outside because it costs less money. Yeah? So, you have the transformer and the pins. Yeah. So you have the triangulation made outside. So it's going to make here. This one. It's going to make it's bad drawing here, but so in fact, if you put the Rogowski here, you measure 0. And because the current is going from here from this side and here from the other side. So you measure 0.
Some current is gel, so the lowest will indicate the gel. Some of this current and this current is cancel out, so
Yeah.
you say
Yeah. So in fact, you have to install the after the triangulation. You have to install it here. Yeah. And here. And here. Alright? Not directly in the transformer. Pay attention because I know a lot of, let's say, professional electricians, they've installed most of the time the Kowarovsky coil like that. Yeah, that's why I point out, yeah. Okay?
Is there enough space to install the lowest coil?
Yeah, that's why sometimes you have room enough in the transformer room to do it inside. Otherwise, you have to put it outside. Yeah. But with the, let's say, the high temperature protection for cables right now is no more problem to install it outside. Yeah.
저거는 나중에 뭐야 저 신재강 트랜스포머건 서양 오류 때문에 된 자료가 있거든. 그 자료 보면 어떻게 그 외가 아웃도어 대작품을 좀 만드는지 그 형상을 봐야지 기대하는 사람들 이해가 좀 될 것 같아.
Well, so this was for the current, and here you have the voltage. Voltage is also taken on a bus bar. Better not on the electrode arm. Here, not here. I know some people who wanted to have the voltage measurement as close as possible from the electrode tip, but you get so much noise and mutual influence when you measure on the electrode arm that it's better to measure it on the bus bar.
이 책에서 보면 전류 측정 전압 측정인가 TR 전단에 있잖아. 전류가 TR 일렉트로 앞쪽에 있고 이렇게 돼 있잖아. 근데 지금 로스쿨 온다면은 뒤쪽보다 앞쪽에 설치해서 전류하고 전압을 그러니까 일렉트로 앞하고 TR 사이다 측정하는 거예요. 그지?
정확한 컨트롤을 위해서 제가 알기로는 2차 측에 설치하는 게 좋다고.
그지? 그걸 맞는데 옛날에는 로스쿨이 나오기 전에는 앞에
그게
책에
그 아까 말씀하신 것처럼 1차 측에다 해야만
아니, 그치.
1차 측은 그러니까 전류가 적기 때문에
아니 내 얘기가 그 얘기 아니고 기계 전문가들을 보면 하는 얘기라고 하면 책에서 보면 TT를 전류하고 전압이 다 TR을 주로 전 구간에서 측정이 되어 있는데 그거랑 지금 하는 얘기랑 헷갈리지 말라는 얘기라는 거예요. 전기하는 사람들은 굳이 내가 얘기 안 해도 뭐 다 알고. 오케이, 이거
저도 보스바에서 전
So then you are coming into the hardware of the electrode regulator with the analog inputs, the regulator itself, and the output cards, which are going to the valves, yeah? And with the HMI here, and connection with the other, let's say, EAF system as level one network.
How about the install the regulator system in main PLC? Do you have
No.
some?
No.
Some?
No.
No?
No, because then it's the program is very huge, and you have to have fast function for this. So it's better to have it split out of the main.
All the PLC card is used for specific use for fast response in this regulator system
Yeah.
compared to general.
Especially here, these I/O cards, yeah, they are very fast. Yeah.
You mean the analog AI and AOs use the other card?
Rather, I mean,
Comparing
right
the
now,
PLC?
the Siemens PLC has a very fast, let's say, cycle loop. I guess it's 10 milliseconds or so, which is enough for the regulator function itself, but not for the measurements here.
그게 무슨 얘기예요?
그러니까 일반 PLC 카드는 이거를 전 AC/DC 바꾸려면은 뭐 커런트가 바뀌는 가장 빠른 프리퀀시 2배 이상의 샘플링 주기로 이렇게 그 샘플링 해야 되는데 저 일반적인 그 IO 카드는 그렇게 샘플링 타임을 그렇게 빨리 할 수가 없거든요. 요거는 스페시픽한 농도의 카드를 썼기 때문에 그걸 따라갈 수 있거든요.
So that's why usually with standard Siemens equipment, we have here for the measurement a specific, let's say, small PLC, which is called VIPA, V-I-P-A, yeah, which has enough acquisition speed for the measurement. I guess the cycle time is, I don't remember.
Vipa? What is it?
VIPA,
Vipa?
V-I-P-A.
What's that?
I Siemens. I'm not Siemens specialist. Because this equipment is changing very fast. So
This secondary voltage is measured refer to this point, but this reference voltage point, maybe. The secondary voltage measured refer to this reference point.
yes.
Yeah, but this reference point is somewhat floating.
Is
Because-
what? Is what?
Floating, fluctuation, because there are some mutual inductance between the loop.
Yeah.
So, is there any effect such caused by this floating point to measure the second voltage?
Yes. Let me. Yeah. No, in fact, you see that there is a connection here.
Yes.
Yeah, which is coming there. I'm not a friend of this kind of solution, because then you bring unnecessary noise into your measurement. My recommended solution is somehow different. You can see
Very good response.
it's not very good response. Well, so you have the furnace. What I recommend usually is that on the bottom, this is the bottom from the top. Yeah? I recommend to put here a spider. This is a coil, coil of here 0.5 millimeter thick and 20 millimeter wide. Yeah? On the bottom. Underneath the refractor, you have usually the safety line. Yeah? So you put it on the safety line. And here you have the bricks. And the running mix. Yeah? Okay? So you take the coil and you put it here. Is it clear for you? Huh? No.
Isn't melted?
I start again because the drawing is very bad.
So that means the material installed should be contact with the
Yeah.
steel. I mean, liquid steel.
So this is the safety lining. So you have the walls. Yeah? And here ramming mix. So the coil is installed here. And then on the bottom, up and going out. And this is connected to the ground.
What material is it, the coil?
Steel.
Steel?
So it can be melted by the
Yeah, sure. But this is, I mean, whatever it's meant, because then you have, let's say, steel infiltration, and the refractory is driving the neutral point. This is to ensure good contact for the first, let's say, heats. Yeah. To have a good neutral point.
But after repairing the small part of the refractory,
I mean,
and then
what do you repair? What do you repair the banks and you repair the upper bricks. Yeah. So I mean, later, it's not critical because you all the time have some infiltration. Of course, if you destroy all refractory and reinstall it completely new, it's better to install this contact again.
the bottom side also is also the refractory
Right?
bottom. This is refractory. What is this? What is this?
Ramming mix.
Ceramics?
Ramming mix.
Long mix?
This is the half of the furnace. On the bottom, usually you don't have bricks. Yeah? It's a sand which is sintered later.
I saw that here is refractory.
Or if you have refractory on top of the bricks, on top of the bricks you have all the time some ramming mix. So if you have bricks, yeah, it's rather easy to understand.
Yeah.
You put it okay like that. That's it. You have all the time some ramming mix on top of the
Yeah,
bricks.
we call it castable.
No, castable is totally different.
Totally different. Loving mix?
Castable is
First
totally
spelling.
different.
Spelling loving mix?
Castable is like concrete,
Yes, in mortar.
mortar, and you never put such mortar in a furnace.
If you're loving mix, I didn't
It's like the sand.
What's the meaning of the
ground.
So it means that we need to audition column 2. I mean, dig the ground and
Oh yes. Anyway, the furnace is all the time grounded to avoid arcing between panels. Yeah? So this is the same ground. You have one special ground for the furnace. The shell and the roof. Yeah?
okay.
Sure. Even for other furnace, you have to have a ground. Yeah?
전략하면 저 대차나 전부 뭐 저기도 마찬가지고 끌어내가 접촉을 시키잖아.
Yeah.
Huh?
So what is the benefit of this? I mean, the contacting the steel with the ground. What is the benefit? Compared
The benefit is to fix the neutral point. Otherwise, the neutral point may vary quite a lot. Huh?
So you mean the Louis, some kind of Louis?
다른 경우는 철피 쪽 접지를 해서 가져오는 거 아니야?
네, 그러니까 제가 물어보고 싶은 게 저렇게 하는 거랑 저렇게 하는 거랑.
지금 직접 형태하고 전체 이 5 델타 만들어서 가져온 거에서 뭐 5 보였던가 해서 좀 더 바로 1차 접촉하는 개념으로 가진다 그런 얘기 한 것 같은데 아까?
그러니까 그게 뭐 노이즈.
아까 설명을 여기까지
계속 해요.
이렇게.
This advantage is to fix the neutral point here. Whatever happens here, the triangle may vary, but this neutral point stays in the middle. Otherwise, it's moving in a wide range.
So as a result,
I have seen whenever I made measurements on furnace, taking there were no grounding. Yeah? I took a voltmeter between the shell and the ground, and I saw up to 80 volts. Huh?
So, what is the effect of that
The effect is to fix the neutral point
on ECS system? If
that you can measure. You can
볼트
measure
매진하기 위해서
the voltage with good accuracy. Yeah, without neutral influence.
그러니까
Yes, please.
그래요. 지금 우리는 2차 전압, 2차 볼티지 이걸 정확히 측정해야 컨트롤을 제대로 할 수 있다고. 그럼 이거 갖고 이제 아크 저항 이런 것까지, 아크 디스턴스까지 했는데 이게 흔들릴 수 있다고. 이게 아까 말했듯이 그 뮤추얼 그 인덕턴스 해갖고 이렇게 플로팅할 수 있다고. 이게 기준점 흔들리면 이게 어떻게 정확한 감이 나올 수 있다고.
결과적으로 저게 이제 ECS 시스템에는 노이즈처럼 느껴질 수 있어요.
아니 이거를 픽스 시켜놔야 이걸 기준적으로 픽스 시켜놔야 여기에 대해서 이게 100볼트다 200볼트다 정확히 측정이 되잖아. 그걸 가지고 이제 정확한 측정까지 돼야 이제 정확한 컨트롤을 할 수 있다는 거지. 그런데 이거는 이렇게 접지를 안 하면 이 사이에 있잖아. 이 사이에 뮤추얼 컨덕턴스가 있고 이 볼티지가 뜬다고 그게 변한다고 자꾸. 그럼 이게 변한다고. 그럼 이 값은 이 기준이 변한 값을 가지고 측정을 해봐야 컨트롤 해봐야 아무 소용이 없는 거지.
Yeah. Okay. And don't forget that the potential is defined between two phases. It's not defined between phase and earth. If you put a piece of a bridge, it's a cable between one phase and the ground, there is no current going through. Yeah? You just fix the potential of this electrode to zero, to the ground.
네, 그럼
You
결국
understand?
스틸하고 저렇게 밑에 접지시키는 거는 결국에 스틸 면의 전압 위상을 접지면에 있는 위상.
이거는 그라운드는 항상 제로로 돼 있다고. 이거하고 그러니까 이거하고 선으로 연결됐다는 이거하고 똑같은 정의로 만들어준다는.
그래 그런 게 맞죠.
그래.
So this ground is the same as for the furnace, yeah? No need to have a special ground.
Yes.
But for the regulator, need a special ground.
Okay.
Huh? So you have here the voltage with the voltage transformer that goes to the regulator. Huh? So here you have three pieces. So in this case, what I suggest each time is to connect the neutral point, primary and secondary.
Star connection. Star connection.
Yeah.
Why you recommend the star connection?
To fix the neutral point and to have accuracy. And this is dedicated
The ECS system.
to the regulator.
Yes.
Don't put other MCC or
Okay.
whatever.
Okay.
Yeah.
Should we connect it with that below one? The ground point,
Eh?
upper one should be connected with the below one.
다른 거죠?
똑같은 거예요.
저게 저거랑
똑같아야죠.
저게 자체예요?
똑같아야죠.
Should we
저거 요거하고
be
저거하고
disconnected with?
저건 dedicated only.
이거하고 똑같은 거예요.
Yeah.
근데
저거
저거
연결을 안 했나?
Yeah.
다른 거잖아.
똑같이 dedicated.
Separate.
아니요.
There is just one ground for the regulator, and there is only the regulator on this ground.
저거는
시야를 두고는 저쪽 별도에서 하나가 접히고 이쪽은 LF 같으면 대차적을 연결해서 접촉시키고 전기로 같으면 본체 뽑아서 그런 데를 시킨다고.
No.
아니야.
그거 아니라는데요. 저 그래서 여쭤본 거.
그 별도야 별도. 같이 할 수가 없지. 저거는 지금 TRC를
No.
만들었다고
This is standard. This is the worst.
This is
This
general,
is
general, and this is specific for ECS. Okay.
그게 무슨 차이예요? 의미 차이예요?
이거는 이만은 그 MCC랑 워낙 모든 그 트렌드 전체 공통 카문 기준을 삼는 거고 이거는 이 자체 only 이 자체 ECS 전용으로.
그러니까 쉽게 얘기하면
왜 그래요?
아니 연실들이 생각하면 뭐냐면
Because even on this ground, you may have a lot of pollution from magnetic field, which you don't want to know. This is only, let's say, the bath stuff. What you want is to have the arc fixture, and for the arc fixture, it's better to have a clean neutral point, independently from all kind of noise you have down there.
이게 쉽게 얘기하면 저 보내는 쪽이 있잖아요. 들어가는 쪽. 그 제일 좋은 건 정보 측정하면 제일 좋은데 정보 측정할 방법이 없잖아. 그래서 뭐 전기로나 LF에 그 나오 그 묻어놓은 접지 쪽을 통해서 다시 아까 그러니까 인풋 아웃풋을 서로 비교해 본다라고 생각을 하고 얘기를 하고.
접지도 전해를 좀 가질 수 있잖아요. 변하면서 그렇죠.
아 이제 접지라는 건 그 전자가 엄청나게 있는 거예요, 그냥. 그러니까 등전이지.
그런데 걔도 절대적으로 처리를 할 수는
그런데
없잖아요.
아주
바닥에 영향이
바닷-
크게 가면 안 되니까.
바닷물이 아주 큰 바닷물이 있는데 거기에서 물이 하나 샌다고 이게 거의 안 변하잖아요. 그런 수준의 그 그라운드 제로거든요.
그렇게 맞죠.
그거 같이 하면
아니
문제.
저기서 미세하게 들어가면 안 돼. 왜냐면 그냥 이 정도의 오염치를 두고 이걸 제로라고 본다라고 보고 가야 되는데 거기서 자꾸 그 디테일하게 들어가 버리면 이제 진동.
아니 나누는 이유가
너무
그런
그냥
영향이 있기
저거는-
때문에 별개로 나누자는 얘기 아닌가요?
아니 저거는
아니 서로 같이 묶어놓으면 통합버리잖아. 비교 서로 이게 비교가 안 되는 거지.
아니 지금 제가 얘기하고 싶은 물어보고 싶은 게 지금 MCC 접지든 전체적인 제너럴 접지는 어딘가는 전기 설비 때문에 영향을 받을 수 있잖아요,
그렇죠.
그래서
그러니까 그건 저건
미량의
영향을
예,
네.
전압이 있을 수 있기 때문에 그런
네.
영향조차 받지 말자고 별도로
그렇죠.
공부를 한다는 얘기예요.
저거는
네.
그 따로 떨어져 갖고 만드는 거죠. 예, 이거는 매그네틱 필드는 현장에 있지 않습니까? 전류 강한 전류가 흐르면 이제 사이에 이제 전압이 아까 말했던 80볼트까지 뜨거든요. 차이가 80볼트까지 날 수가 있다고.
근데 요즘에는 그런 이제 그 노이즈 때문에 그 MCC하고 PLC하고 인버터 이런 것들도 일부는 별도로 접지를 한다고. 그러니까 이것도 마찬가지로 현장에 설치할 때는 요거 별도로 이렇게 접지를 해주거든.
내가 모르는 거 하는 거 모르고 뉴트럴이라는 게 있지 않습니까? 항상 현장 보면 접지 따로 있고 뉴트럴 따로 있더라고요. 얘기를 보니까 그것도 뉴트럴도 접지 개념이 맞죠? 그렇죠?
뉴트럴은 하여튼 레퍼런스를 잡는데 뉴트럴을 10볼트하고 연결하면 그게 뉴트럴이 10볼트 되는 거고
네.
그라운드 제로하고 연결되면 제로가 되는 거예요.
저기 접지고.
예. 아까 말 뉴트럴은 그 델타 쪽에 이게 어떤 전압이란 거 항상 기준되는 걸 가지고 어떤 포인트를 가지고 해야 되는데 이게 제로 볼트에 연결되면 이게 기준이 제로가 되는 거고 5볼트에 연결되면 5볼트가 되는 그런 거예요.
아직 잘 이해가 안 가네.
아니, 그러니까 쉽게 생각하면 보통 현장에서는 저것도 다른 거랑 같이 묶지는 않고 저것도 별도로 떼. 요 밑에 전기로나 빼는 쪽 있잖아. 그것도 별도 떼고 저것도 별도 떼가지고.
아, 나도 옛날에 그 하여튼 뭐 뉴트럴이 제대로 나오네 안 나오네 하고 막 시끄러웠던 기억이 나는데 잘 이해를 못 하겠더라고요 그때.
저도 그거라 정확한 걸 깊이 들어가지 않다면 저도 확실히
근데 한 번 더 물어보는데 왜 그 나는지.
물어봐 다시.
Could you give me the
Could you
detailed
explain
information about
one more time why we divide the
I mean, you don't need to know. You just have to do.
이게 이제 문제적으로 시작이다.
Because, I mean, in Indonesia, for example, they have installed the regulator and they have connected the ground to other MCC. We got disaster.
Yeah.
So I asked them now, we stop the furnace operation and you install the correct grounding for the regulator. So this is independent, and there is only the regulator on this ground. We need accuracy. We don't need noise from anybody else. Yeah?
지금 기본적으로 떨어져야 되는 거리도가 있죠. 그러려면
예.
기본적으로 떨어져 있어야
예.
되는 거리도.
그렇죠. 그리고 저게 Y 결선이라는 게 그게 중요해요. Y 결선을 하면은 그라운드를 이렇게 끌어낼 수 있거든요. 이제 Y 결선이 있거든. 델타 Y 결선 이런 걸 일단 내가 다시 한번 설명해 줄게요.
아니 일단은 책을 좀 봐봐. 그 LG 책을 보면 모타 책 있거든. 그 책을 보면 거기 잘 설명 쓰는 공부해야 돼. 봐도 설명 듣고 봐도 맨날 잊어버려 안 되는 거야.
델타를 하면 델타 결선하면 프로틴데 그러니까 Y 결선하면 그 그라운드를 끌어낼 포인트가 생긴다고요. 그래갖고 그 포인트를 갖고 전출하는 거예요.
Y 델타를 해야 되는 거 아니야?
Y 결선 있잖아요.
Y로 말해. Y 결승 뭔가요?
Y 결선
Y
Y
결승
결선
나 지금 Y가 있고 델타 있고 Y 델타도 있고 스타 있고 그렇잖아.
그 1차는 델타를 했잖아요. 1차는 델타고
그래.
2차 쪽에 저것도
이차 쪽에.
PT로 Y 결선해갖고 그 Y의 이제 중성점을
그렇지,
이렇게
그렇지.
그라운드를 끌었다고. 그래갖고 그 포인트 기준점 안 변하게 만드는 거예요.
일단 넘어가서 나중에 물어봐서.
너무 디테일한 부분 이시에서 집중을 좀 해야 돼.
오케이.
시간이 너무 없을 수도 있으니까 끝나고 마지막 날 또 질문해야 되니까 적어놨다가 얘기를 좀 해보고. 근데 이런 설치 조건이나 이런 부분들은 다 알아야 되는 부분이니까 대놓고 이론적인 부분들은 조금 뒤에 따로 물어본다면 이런 의미는 일단 물어보는 게 하는 게 나을 것 같아요.
아까 바이파가 뭐라 그랬어요? 컨트롤하니까 바이파가.
PLC 카드.
요 카드 기종이에요.
예, 예.
근데 이게 PLC가 그냥 범용하는 거 지면서 이런 거 사가지고 우리가 개발한 소프트웨어를 설치해서 쓸 수 있는
아니 아까 말한 스캔 타임이 있잖아요.
그런 게 구할 수 있으면
그렇죠. 그렇지.
커런트는 아주 아크 쪽에 커런트 아주 빨리 변한다고 프리퀀시가 아주 빨리 빨라요. 그러니까 거기에 최대 프리퀀시의 2배 이상의 샘플링으로 해야 나중에 ADDA 컴퓨터했을 때 디스토션이 안 생긴다고. 그럼 그런 캐패시티의 카드가 있어야 되거든.
사양에 맞는 거 사면 된다.
그냥 살 수 있다는 거죠.
패스트 카드.
어제도 얘기했잖아. 소프트웨어 저희가 하고 하드웨어 우리가 사면 된다고 하면서 지금 카드는 사볼 수 있는 거니까 하드웨어는 문제가 없고.
오케이.
Okay, so now we are coming to the general layout of the regulator. This is the structure of the program. So you have the measurements here with the what we have seen just before, and the electrical calculation, let's say. And then here we compare this, let's say, measurement to the set points, and we are going into the PI, the regulator, which is making the translation between the error, that means the signal minus the set point, and transform it to something that will be sending to the veil. Then we have additional here precondition we will see later, and we are going here to a limiter and acceleration limiter, and we go to the veil. These are filters, let's say here, and we go directly to the veils. So what else do we have here? In a furnace we have three different situations, or mainly two, yeah. Because this current limiter, I don't suggest you to do it. So you have the ignition. That means ignition, we will see what is later, but this is the situation where you have no arc. So, and the electrodes try to ignite an arc. So you have a special, let's say, features for this. And short circuit, you have the electrode in contact with the scrap or the bath, and it's again a special situation compared to the normal, let's say, regulator. And we may have here, let's say, some smart function, which are the dynamic set points modification to, let's say, change the set point or arc length according to the, let's say, process status. We will see how to do it. Okay? So these are the measurements. We get here the 3 currents, 3 voltage, and eventually primary voltage. And first thing is to transform the signal coming from the Rogowski coil or from the CTs into the RMS. No? And then we take the voltage and the current and we multiply the scan values directly to calculate the active power. Yeah? This is realized with the scan values to consider all the harmonics. We don't take this IRMS multiplied by the URMS. It would be a mistake. Yeah? So we calculate the RMS value of the voltage and this is the star. This is the ground to phase voltage, and this is the phase to phase voltage. As another input, we have 3 hydraulic pressure. Yeah, to have the touchdown correction. The touchdown correction is not shown here, but it's coming here. In this area, we will see later.
저기 용어에 대한 설명이 따로 기입 안 돼 있을지는 보니까 그런 것 같은데. And next time I think the diagonals shall be modified because the symbols, letters, there's no explanation. Only C, E, L, only electrical position only.
What?
The RMS you said to the face-to-face voltage, but I don't know
You don't know, so you ask electrical people. They know.
I think electrical people also doesn't know what the meaning of it is. So write down the like the G or P hydraulic.
This is explained here.
Need the explanation.
G means position.
Electrode position is for a special function we will see later. So then you go into all the calculated parameters, yeah, which is well known. You take a book, electrical book, you can find it.
This method may be followed by the common method to assume the operating reactance.
This is the operational reactance.
This method may be created by the Bauer. Maybe Bauer method. Maybe there are several methods to get the operating reactance, but it is one of the methods created by Bauer.
No.
Is this general? Is this general? Okay. Not specialized by Bowman. It's general.
I mean, this is older than Bowman. I mean, I guess in the 60s already, people have noticed that the arc stability is proportional to this K factor.
Yes.
Of course, when you read a book from Bowman, you will take again this stuff, but I mean, this is existing since 50 years.
Yes. What is the range of K factor? Maybe K factor maybe can be more than 1.
K is more than 1. Cannot be lower than 1.
It includes the short circuit reactance in the operating range. It means
No. Look, operating reactance. This is this formula.
yes.
Okay.
But what I say is G in this value the short circuit reactance is included.
Of course, cannot be off.
So this in the operating range it is included also.
Of course, yeah.
I
I mean, we are not measuring the voltage at the tip of the electrode. Eh?
Okay.
the measuring point, it doesn't change.
Mhm.
It's still the same. So you have the short circuit impedance inside.
그것도 너무 좀
On site, the real actual value of short circuit reactance is measured on site.
Yes.
Do you have any experience to measure such value on site?
I mean, 2,000 million times, yes, I mean. I mean, this is there's nothing special, yeah?
Is there any difference between the measured value and the calculated value?
There is no calculated value.
Assumed value by the factor.
On this
Yes.
parameter, it's not possible to calculate the value. You can estimate the value.
Yes, I mean the gap between estimate value and the real measured value on site. There's many big difference.
20% maybe.
20%.
쇼트 리액턴스가 에스티메이트 된 거랑 실제랑 29 차이 나는데
오케이. 그 있으면 봐.
저기 저 인테그레이터 있지 않습니까? 저거는
직접
제가 실제로 구현할 때 저
어.
인테그레이터를 뭐 구현돼 있는 거 갖다 쓰면 되는 겁니다.
인테그레이트.
그 위에 보면 저 펑션
저그 PLC 펑션에 인테그레이트한 펑션이 있지.
이미 구현돼 있습니다.
응.
갖다 쓰기만 하면 됩니다.
그래도 어떤 사람들은 또 직접 만들었을 때 이형 자체를 돈 주고 사야 되거든. 이게 펑션이 있는 것도 있고 또 돈을 추가적으로 사야 되는 게 있거든. 자체가. 그러니까 이제 어떤 사람들은 만들었을 사람이 있고 어떤 사람은 사는 게 있고.
Should the integration function on top of this document can be used by, I mean, implemented by one PLC program? Or
Of course, it's done by a PLC. What else?
does it need something special function for the ECS system for this?
What is
integration?
important? What is important is to have this with let's say a good frequency. That's why at the end of the document, I have had this recommendation here. 10 kilohertz. Yeah. To have enough sampling.
이 샘플링 셔.
Yeah.
그러면 그 프로그래밍이 다 돼 있으면 우리가 이거 실제로 프로그래밍 할 때 크게 뭐 갖다 블록을 갖다 쓰고
우리가 할 수 있는 셋 포인트 밸류 뒤에 나오지 않은 그런 컨피규레이션만 잘해주면 돼. 그리고 거기에 따라 패러미터만 정확히 이제 옵티마이징 하면 되고 이 사이트에서.
프로그래밍 할 때 그러니까 아주 뭐 어렵지는 않을 것 같아요.
근데 이 알고리즘을 실소스나 구현하는 게 어렵지. 거기 있는 갖다 쓰는 펑션이야 뭐 다 있는데 뭐 어렵게 보면.
So if you don't have, let's say, a fast acquisition device, yeah, you don't get a good result. You cannot run the regulator.
오케이.
Yeah.
샘플링 시험 배웠지. 옛날에 있잖아.
At least you can run, let's say, a very simple regulator to move the electrodes, but don't expect to have, let's say, a lot of possibility to make optimization, to find the best working point. Because to find the best working point is not a science. You have to make experiment. So you put, let's say, set points inside, and you expect to have the electrical calculation and average figures of the heat, and you can make comparison. I change this parameter, I get this result. If you don't have good measurements, you cannot see the results. So you don't know where you are.
Okay.
You are just working blind. It's possible to have, let's say, a very slow measurement device, but then forget to have any possibility of optimization. And this is not nowadays something that costs a lot of money.
At this moment, I have another question for you. As you said before, you said that there is no way to measure the arc physics,
Yeah.
but we can calculate the arc
Yes.
physics.
Yes.
So that means that we can use the closed loop by calculation of arc physics, right?
Mm.
So then why don't you use the closed loop instead of open loop?
Because you're not regulating the arc length.
But we can calculate.
We are regulating the electrode speed.
Only regulating speed. 맞습니까?
아크램프가 뭔지 정확히 정의가 뭔지 알아요. 아크램프는 정의는 이 팁하고 요건 사이의 길이라고. 그런데 아크램프가 다이렉트로 이러는 게 아니고 이게 일로 되든 저로 되든 이렇게 막 변한다고. 이걸 어떻게 측정해요? 우리가 측정할 수 있는 건 정의라고. 이 팁하고 요건 사이의 거리를 그렇게 정의한다는 거지.
근데 지금
실제 아크가 길이가 어떻게 되는지, 각도가 어떻게 되는지는 측정 못하지.
네, 근데 여기서 이제 출력되는 게 뭐죠? 스피드로 한다는 게
스피드는 아크 포지션을 얘기해. 아크 포지션.
그러니까
아크
does the output is the position or between position or speed? You said that we can control the speed of the regulation. I think that we control the position of the electrode, right? So, but you said that we control the speed of the
No, we can install measurement. The position measurement. But you don't know how can you know the electrode, the arc length? You cannot know.
So
You cannot measure the arc length. You know the electrode position, but the mass position, this you know. But the electrode length first you don't know. And the distance between the tip and the scrap is changing very fast.
So
Because on scrap, when the arc is on scrap, the scrap is disappearing, it's vaporized. And when you are on the bath, you have bath movements, you have projection and stuff. You never know the arc length. You cannot know.
yeah, so
And the arc is all the time moving. How can you measure?
okay, then the Y value on the layout you showed on this document.
Mhm.
The Y value means that the speed of regulation, right?
No. This is the signal
Signal for
sent to the valve. This is something which varies between minus plus 10 volts and corresponding to 100%
the
opening.
signal for the controlling the valve.
Yes.
So it says don't know the position.
이제는 포지션
No, we may measure the position of the mass, but we don't use this parameter for regulation.
스피드를 한다는 건
시간이 별로 안 걸리니까 좀 설명해 줘.
You have understood? We measure the position of the mast. But the mast is moving up and down. You don't know the electrode column length. You don't measure.
절대적인 포지션은 모르고
The electrode is getting shorter and shorter as long as you work. Yeah. Okay.
Okay.
And when you get into the scrap, you don't know where is the scrap. There is no way to measure. Yeah.
I see.
근데 높이를 계산하는 방식이 하나 있어. 뭐지? 루트 3분의 루트 있잖아. 540V 해가지고 그에다가 빼기 코사인 파이하고 플러스가 코사인 파이하고 여기서 마이너스 코사인 파이구나 해서 플러스 40 이렇게 하면 그렇게 하면 계산치로는 이 이 지금 이제 높이가 어느 정도 돼 있다 이렇게 계산을 하는데 실제 그거랑 엔코더 값이랑 막 움직이는 거 보면 계산치가 좀 틀리더라고요. 자체가. 그게 그렇게 해서 높이라든지 이런 측정하는 분들이 있거든.
제가 이해한 걸 지금 말씀드리고 넘어갈게요. 저는 저 Y 값이 그 일렉트로드의 위치 값을 신호를 주는 줄 알았는데 그게 아니라 일렉트로드의 위치는 계속 상대적으로 뭐 스크랩의 위치도 변하고 하기
그렇죠.
때문에 위치를 가지고 컨트롤을 하는 게 아니고 그냥 그때마다 그냥 얘가 뭐 어느 속도로 뭐 올려야 된다 내려야 된다 그것만 신호를 주는
아니 여기서 아까 뭐야 그 커런트하고 볼티지 그거밖에 모른다. 그걸 가지고 이제 다른 거 다 맡겨 있어. 그거밖에 빛이 안 보인다고. 그걸 가지고 이제 내가 이렇게 올라갔다 내려갔다 하는 거야.
밸브를 가지고
밸브는 갖고 결국은 뭐 그래서
강렬한
알수 있는
아이디어도
저밖에
되는
없잖아.
거잖아요.
클런트를 세팅해놓고 그게 뭐 예를 들어서 내가 하는 저기 보면 조종하는 두 개 있잖아. 렉팅 조종하는 두 개. 하나가 많이 울리는 것도 있고 조금 울리는 게 있거든. 그래서 내가 가지고 있는 거에서 기준점에서 몇 프로가 위냐 아래냐 그거를 가지고 속도를 빨리 올 거냐 늦게 올 거냐 뭐 이런 조종들을 하는 거지.
이해했습니다.
저게 재밌네.
뭐